Entropy and Gibbs free energy. Remember all that?
No.
And then if you don't, then we went through entropy and Gibbs free energy. Yeah. But the last part of the chapter deals with Gibbs free energy and equilibrium constants. And we didn't go that far because you haven't had equilibrium constants. So I will go quickly through this. I'm not going to leave you enough time to write these things down, but it's a refresher on here's entropy. Okay, remember entropy is a measurement of randomness. Do you remember microstates?
They wiggle.
Wiggle.
That's all I
Remember
got.
what I used to show you the wiggle?
The guy doing
The floss.
Yep.
There's all this stuff on entropy.
Kind of like
This is all from before. Entropy of the universe is always increasing. Boltzmann talked about microstates. Entropy, right?
Let him go.
Microstates.
I mean, it's really impressive, to be honest. Like, I can't.
I can. But that was because I
His
actually
face kind of looks like Squidward.
like could get out smile.
Yeah.
Anyway, there you go. So microstates, are you good with microstates?
Sure.
And then remember that you can skip all these, skip all of this. Are you good with this? You read it. That as you do things like increase temperature, you increase entropy because molecules or atoms will move around more. If you increase the volume, there's much more space for them to move. And if you add more molecules to a sample, you have an increased number of possible states because you have more moving molecules.
What about pressure?
If you put them under pressure, you force them closer together.
What doesn't cause
Okay. Remember states, things like liquids have more entropy than solids and gases have more entropy. Yeah, again, okay. Solutions, changes. Let's go down to skip all of these. Third law of thermodynamics. And this equation becomes important. Remember this? Change in entropy, sum of the entropy of the products minus the sum of the entropy of the reactants. Okay. You have this
N is
equation.
moles.
Yeah, N and M are the number of moles of each one. Okay. This is just like the delta H equation from 161. Okay.
I do not remember.
So if I put an H in for the S's,
And it's the same thing.
it's the same thing.
What is H again?
M, heat.
Heat.
S is entropy, movement. Okay. All right, so I'm gonna move to this one, just skip that. That's the universe increases. And then Gibbs free energy, do you remember this?
Yeah.
Okay. And remember that when delta G is negative, you have a spontaneous process. If delta G is 0, you remember that? How about if delta G is positive?
Oh wait, this is at equilibrium if delta G equals 0. If delta G is positive, it's spontaneous.
Non-spontaneous. Right.
Hold up.
Right there. Look at that.
She's reading out her notes, she's cheating.
She's not cheating, that means she has good notes. Go Victoria notes. Huh?
I could have done that. It's
Where
not
you-
gonna matter when you don't have the notes on the test.
So where are your notes?
In my notebook,
With you?
I still look at them.
Okay, so you've got these three possible conditions. Delta G negative, you get forward spontaneous. 0 is at equilibrium. Positive means it's non-spontaneous in the forward direction, but it's spontaneous reverse. Okay.
Wait. You just said.
Delta G is negative, so when you
No.
do calculation
Delta G positive, it's non-spontaneous
in the
one
forward
direction.
but it's spontaneous in the reverse.
Okay.
Okay? All right. So this would be a good thing to know.
Got it.
Alright. And this is a 162 slide.
Sure.
This is not the material. And if you don't remember from 162,
How long have you been teaching this?
long time.
So you teach
Probably
this.
longer than you've been alive.
Like, yeah, exactly. So you gotta cut us some slack. Because we've been learning this for like not even a year.
I know.
And you've been teaching it for like
Forever.
lots of years.
Forever.
Forever. Be nice to us.
You get to be old like me, you start forgetting things.
I pay you to be nice to me.
Oh. You don't pay me. You pay somebody else and then I get like a sliver of what you pay.
I still pay for you. Just that sliver.
I get $1 out of your tuition.
I mean,
And you had like $300 for your education.
huh?
So did I get like $1 of your tuition money? You got
Okay,
like $300.
this is a 5-credit class, and for 5 credits, it's $525. And then there's like a $17 lab fee or something.
Right.
There's no way you make $1 out of that.
Pretty close.
No.
Alright, maybe $2.
Well, it's not enough for like an entire quarter of teaching.
Yeah, if you take all y'all's tuition and add that up and then figure out how much I'm paying out of that, and then divide that by the number of students,
Why would you?
yeah, you're gonna laugh. Because it's not. It's all good though. I try really. And you get this one. That's a good one to know.
So it's just the same freaking thing, 3 times,
Same thing.
telling us different things. What the heck is Gibbs free energy? What does that even mean? I do not recall this.
I cannot make that simple.
I remember the term, but I don't remember anything about it.
Oh, it's right here, Rosalie. And you can think about Gibbs free energy as the energy available to do useful work. Okay? So for this one,
I don't have any of that apparently.
if delta G is negative, the calculation is going to tell you that, at least on a graph like this, you're on the left-hand side, which means you have available energy to move the reaction forward. That's
Yeah.
why you get spontaneous.
And that's
forward
Gibbs.
direction. That's Gibbs free energy. So you can calculate it. If you have at equilibrium, that means here there's no energy to push the reaction one way or the other because it's at equilibrium. Okay. The last condition, if it's positive, that's on this side. We say that your reaction's already basically gone forward. Now you've got no more forward movement. There's no energy available to push it forward. But you've got energy to push the reaction backwards. So that's why when you have a positive delta G, it's non-spontaneous forward.
How do you have negative energy?
You don't have negative energy. You have a sign that tells you something about
The
the
direction in which
availability.
it flows.
It's like, and this is something to remember, that when you guys look at a negative delta H versus a positive delta H, remember that, think about this as heat. It doesn't mean
In or
negative
out?
heat, that means heat going out. This means heat going in. So if you're looking at negative delta G, that means available energy to move forward. If you've got positive delta G, that means energy available to move backwards. That's the way you need to think about positive and negative, not in terms of negative energy and positive energy, or negative heat, positive heat. It's even like when you calculate Q, you can get Q negative and you can get Q positive. What does that tell you about endo versus exothermic? Exothermic energy out, endothermic energy in. It's not negative energy and positive energy. The sign tells you something about availability and direction.
Okay.
It's not a handout.
So is it safe to assume that this is like potential energy, Gibbs free energy?
You can think about it that way. It's going to be, yeah.
So now, what's the spontaneous mean? What does it mean? It's spontaneous.
So like you
it
take a
just
look,
does it.
it just does it. Like
You can't make it do
you
it.
put a piece of iron outside, what happens to the iron?
It probably will rust.
And that's a spontaneous occurrence. I mean, you don't have to do anything. The iron's outside and it's got some oxygen.
So meaning it's gonna do it whether you do something to it or not.
Sometimes, but here's the question, can you run that reaction, like get that, you take that rusted nail, can you run it backwards and get the original?
No.
No, it's spontaneous in one direction. Increases the entropy of the universe. You can't run it backwards without putting energy into it. You didn't take these things, what's the direction for the battery in here? To drain it.
Yeah.
In order to make this go backwards, you gotta plug it into the wall and put energy back into the system. It's a spontaneous one direction.
So is spontaneous
This
not,
battery does not spontaneously recharge.
so spontaneous in this sense isn't the spontaneous. Not the word that we would use. Like,
Not like spontaneous, hey, let's go out and do this tonight. No, this is spontaneous, meaning it occurs without any outside influence.
okay,
Okay? All right.
I think I'm good on that.
Do you remember this equation?
Mildly. T is
Temperature.
temperature.
A couple things that I want to mention, at least with respect to this equation, because it does show up. Enthalpy measurements are in kilojoules. Entropy measurements are in joules. Okay. When you do a calculation with this equation, you've got to remember to convert, and really you just convert the entropy term into joule or kilojoules. So think back to the delta S equals the sum of the delta S minus the sum of the delta S. All those values are in joules. Okay.
Do you know why it has the degree symbol?
Standard temperature and pressure. There's 1 atmosphere, 25 C. And then for what's coming up in a minute, 1 molar concentration. So,
Okay.
Amber.
When I was looking at the ACS exam, when they were using standard temperature pressure, they need 0 degrees Celsius.
That's what
Yeah.
my physics teacher said too.
Is that gonna be problematic?
No, no problem.
So,
You need the wrong
It's
answer.
supposed to be 0 or it's supposed to be 0.5?
I'll check on that and have an answer for you. Very
So
frequently.
how
which
does
one's
delta G
kilojoules
change
and which one's
temperature?
joules?
So think about the terms. If you make a temperature number a bigger number, and you're subtracting it,
So it's gonna be small.
you gotta think about it in terms of how does the reaction behave or the equation behave. The
So
math.
more temperature,
So if you make this number bigger, you subtract a larger number.
smaller.
Right, because it's gonna assume you know.
And you've also got to pay attention to the entropy term. So if entropy is a positive, you're subtracting a larger positive number. If the entropy term is negative, which does happen sometimes, now you're subtracting a larger negative number. Then you got to think about what happens if delta H is positive or negative. So if it's a negative minus a large positive,
So we cannot make an assumption of what happens to delta G based on just temperature.
not exactly.
That's a stupid question. It wasn't my question, it was the slide's question. I was just questioning said question.
He's all full of sass.
We're all starting for questions.
All right. This is not a bad one to look at in terms of how delta G changes with respect to delta H and delta S. Okay. So if you wanted to snap a picture of that one, you can. Trying to get to one equation before. But I figured at least a little bit of refresher. Okay.
Definitely a good,
Definitely what?
a good idea.
What, refresher?
Yeah.
Usually it is. Okay, let's go to, got that one, this one, that one. That was where I stopped from 162. All right, you will want this equation. Zero degrees C for standard temperature. Okay, you want this equation. And then,
Is, what R's are?
this R.
Gas
Okay, so
station.
here, good question, and then something to think about. I'll come back to it.
What are we using this for?
Okay, so you've got two different R values, right?
Yeah.
If you look at that equation, first question, what's delta G measured in? Do you remember?
Joules.
Kilojoules and moles. C measured in kelvins. And then remember that when you're looking at Q, the reaction quotient, you're talking about concentrations, but you don't worry about the concentration terms as an answer for Q. So you got temperature and you got kilojoules. Which R do you use?
8.314.
That one.
That. And the reason is you don't have any atmosphere term in
It's
here.
not pressure dependent.
Right. No pressure term, no atmospheres, no millimeters of mercury. In this case, R is 8.314. And you do need to pay attention to the units because, again, that's going to be in joules. Delta G is typically in kilojoules.
So what that bottom part is telling us is we don't have to worry about the last term at all in standard conditions.
Sometimes.
That's helpful.
And part of it's when you're looking at, well, follow along. So, Rosalie, to answer to your question from before, that does drop out, and then if that turns out to be zero, then this entire term is zero, and you get delta G equals delta G, okay? But not always, because remember that there are different equilibrium constants, okay? And this is the equation that relates Gibbs free energy to equilibrium constants. You'll never be asked to get the derivation on it, so how did you start, how did you get to this point? You don't need to worry about that.
Okay, is it, so it shows a delta G and then the delta G degree sign. Are those two different things?
So this is delta G at not standard conditions. This is delta G at standard conditions. Okay. So if it's at equilibrium, whatever the system is, doesn't have to be standard, then delta G is zero. And that's back to delta G positive, delta G negative, delta G zero. Okay. If that's the case, are you good with this rearrangement?
Is K KSP? Or is K?
Or KC or KP?
Any of them? Okay.
Okay. And then you can rearrange this one more time to get that. So before I go on, is this an okay leap, or do you need to see how you go from here to here?
Is that an I?
It's a slash. Like
Here?
divided by.
Yeah.
Divided. So
Okay. So basically this thing is relating Gibbs free energy to equilibrium. Okay.
So written like that.
And you're gonna give,
You would have, like, if you're asked to solve for K, then you'd have enough information to get delta G, and then you'd have R, you'd have a temperature. Okay. If you were given the equilibrium constant, you could calculate delta G. You could calculate a temperature if you had Okay, in other words, for this particular equation, you'd have of the 1, 2, 3, 4 terms you would have, and that's a constant. So you're really only interested in 3 terms. You have 2 out of 3 terms, calculate the third. If you're asked for the equilibrium constant, calculate it this way. If you're asked for the delta G and you have the equilibrium constant and temperature, you use this one. You could even rearrange this to figure out the temperature term.
Okay.
Pardon? No, I give you that when it comes to testing.
And this is finding the amount of energy that can be used to do something. Right? No?
What is the point of these? Like, what is it telling us?
Okay, so follow along with this one. Try to get this down in the next few minutes, quickly. And Rosa, this will answer the question, what are you going to calculate with, okay?
Mm-hmm.
Okay. So, are you good with the slide as it is?
So we go.
Actually, I'm
Yeah,
gonna-
so add threshold and that must be.
This will take more time than I've got left. So I'm gonna leave this right here. This will be, so we're gonna start bullet point to bullet. Because it will take more than 3 minutes to get through. So buffers, there'll be some multiple choice and there'll be a problem. This will be, I'm hoping short, as in like 40 minutes or less. Seriously?
That's the entire thing.
Meaning like the one from last Thursday, it should have taken you about 40 minutes, 45 minutes. And for the most part, that was true. Some of you took a little longer, but there won't be any acid-base equilibrium specific. It'll be some multiple choice on buffers, it'll be a problem with buffers. I would study the test and then give you tonight. Okay? All right.